Okay, so let's continue our discussion related to PN junction. Last lecture, we had looked at PN junction under forward bias. We had seen why significant current is able to flow in the forward bias direction when P-type semiconductor is made more positive as compared to N-type. And so let's continue with that. Let's look at the current flow mechanism in a little bit more detail as to how current flows here. So just to remind you, on the P side, we have a lot of holes here, very few electrons. On the N side, we have a lot of electrons, obviously, very few holes. And close to the junction, we have a depletion region here. The region is depleted of carriers, which means that the concentration of carriers here is smaller, much smaller than the concentration of holes here or the concentration of electrons here. It doesn't mean that the number of carriers is zero, except that the number of carriers here are much smaller than the doping density. So let's look at so as I said, what happens is when you apply a forward bias here, the forward bias, the voltage here, the contacts are transparent, so the voltage goes all the way to the junction, and the net voltage that you've applied appears across the junction, and what it does is it lowers the electric field, it lowers the effective barrier, and once you lower the effective barrier, diffusion becomes more dominant as compared to drift, and holes and electrons begin to flow. So let's look at that. So I have a hole here, and the hole moves over to the N side. Okay, so the hole moves over to the N side, and now remember what happens is the moment the hole comes here, so this process of hole going from here to here, we call it injection. The hole gets injected from P to the N region. And the moment it comes to the N region, the hole finds plenty of electrons. And so what happens to the hole? It recombines. It recombines here. Now what happens? We are looking for current flow in the external circuit. Now remember what happens is the moment a hole goes from here, this hole that you see here was earlier compensating a negatively charged acceptor atom. Right? The hole was compensating a negatively charged acceptor atom. And as I said, this entire P region was neutral. Now, the moment a hole goes over here, you create a charge imbalance here. So what happens is, note, the hole has gone over here and recombined with electrons. And what happens is, because you create a charge imbalance, a hole gets injected from the contact. A hole gets injected from the contact. So it replenishes the hole that was lost from here. This electron that you see here goes like this and comes over here and replenishes the electron that was lost due to recombination. Okay, so that's how the current flows. Okay, let me go back and see what happens here. So it starts off with a hole here. Hole goes over to the other side, injection. Then you have a process called recombination. And these things are happening simultaneously here. A hole is generated here, or you can say a hole is injected here. This hole replenishes the hole that was lost from P, and this electron replenishes the electron that was lost from here. The net result is what? Net result is you saw that in this wire here, an electron flows from in this region here, which means what? The current actually flows from in this region here. The flow of current is opposite to the flow of electrons. So that's how current is flowing. Internally, it involves injection and recombination that you see here. Externally, of course, electron flows. Okay? Same thing happens here. An electron gets injected from this side. It will recombine with the hole here. And note, an electron comes back to replenish. And similarly, a hole will be created here. Okay? So that's how the current keeps on flowing here. So current flows through a process of injection and recombination here. Injection of holes from P to the N side and recombination here. Injection of electrons from the N side to the P side and recombination here. Okay? And externally, of course, the current flows through the electron. All right. Coming back again to forward bias, as I explained, that when you apply a voltage here, the voltage that you apply here goes all the way and gets dropped across the contact. And as a result, what happens is we said electric field goes down because the applied voltage opposes the built-in field. So the electric field goes down. And you know that electric field results from charge. This electric field is nothing but a line of force starting from this donor atom and terminating on the acceptor atom, right? So if the electric field goes down, it means that the charge in this region will go down. And therefore, what happens is you find that the depletion region shrinks. It becomes smaller. All right. So what you find is that when you apply a forward bias, it reduces the depletion width here. Depletion width narrows. Okay. Now, so application of forward bias reduces depletion width. Now, all of you know that anytime there is a charge and the charge changes in response to voltage, then you have a capacitance. C equal to del Q by del V. Okay. So this is the origin of a capacitance that we call as the junction capacitance, or we also call it the depletion capacitance because it's associated with the depletion region here. So it manifests itself as a capacitance because anytime charge changes, in response to voltage is a capacitance here. Okay. So that's the origin of the well-known capacitance in PN junction, which we call as depletion capacitance because it's associated with depletion region. All right. There's another capacitance in PN junction here. As I've said, that when you forward bias the PN junction, what happens is you are injecting holes into the N region here. And therefore, what do I get? I get excess holes here, excess amount of holes here. The excess amount of holes would be largest here, and then it would keep on decaying because as it recombines, and eventually you'll find none of the excess holes here. Similarly, electrons get injected here to the P side, so you'll find excess electrons on this side here, and as the electron travels, it recombines with holes, and the concentration of excess electron goes down. So what you find is a picture like this here. So this px that I'm denoting is excess holes here. All right. So this excess holes is largest here, and then it decreases. Why does it decrease? Because of recombination. As the holes get injected and they travel in the N region, they recombine. So you get hole density which goes like this here. Similarly, so this is excess hole density. Similarly, this is excess electron density on this side here. Electrons get injected into the P side, and this is the excess electron density. Now, so this is a picture under forward bias because we have injected holes here and we have injected electrons over this side here. Now, note that these holes also carry charge and these electrons also carry charge here. So I have charges, and we call these charges as diffusion charges. In contrast to these charges here, these charges are due to immobile donor atoms and immobile charged acceptor atoms here. So this is a depletion charge here. This one, we call it as a diffusion charge. Why? Because the process which has pushed them over to the N side is a diffusion process here. Okay. So it's the diffusion process which pushes the holes from P to the N here. So these charges have come as a result of a diffusion process. And so this charge, excess charge, we call it as a diffusion charge. And similarly, these electrons, we call it as a diffusion charge on the N side here. Now, obviously, as I apply more voltage, what will happen is more of these charges will get injected. Right? So now what you have is, you have these charges which change in response to voltage, and therefore we have so if we call it QP and QN, these charges change in response to voltage, and therefore we have another capacitance. We have another capacitance, which is the rate of change of these charges with respect to voltage here. And we call that capacitance diffusion capacitance. So note that there are two distinct set of charges here in PN junction. One is this one here, depletion charge, and the other one is these mobile charges or diffusion charge in this side and this side here. Both of these changes change as a function of voltage, and therefore that change manifests itself as a capacitance. Okay, so that results in diffusion capacitance here. So there are two distinct capacitances in a PN junction. All right, let's come back to reverse bias. What happens in the reverse bias? So reverse bias, we'll take P and we'll make it more negative as compared to the N. All right, that's what we're going to do. Now, this is reverse bias here. As I said, this voltage here again will propagate to the junction. And now, what will it do to the electric field? Because negative here, so it's going to enhance the electric field. Right? It's going to enhance the electric field, so electric field becomes larger. If electric field becomes larger, what will happen to depletion width? It increases. Okay? Because note that electric field is directly related to charge here. So I have more charge here, so depletion width increases here. But now let's look at the current flow. In current, we are saying that now because it's negative, we would like the current to flow in this direction. Because negative means current should flow from N to P. Now, if we want current to flow from in this direction, we are asking holes to flow in this direction here, from right to left here. And we are asking electrons to flow opposite to the direction of current from left to right here. Now you can see the trouble. You're asking holes to flow from right to left. Now, is it easy for holes to flow from right to left? Easy or not? Of course it's easy. Why? Why would you say that? The electric field helps here, right? Yeah, concentration is low, but electric field helps, right? So if a hole, let's say, is able to reach this region, then the hole will be simply able to flow. Right? So it's not that the electric field earlier in forward bias was opposing and diffusion was what was pushing it. Now electric field helps in movement of holes from this to this side. But note, how many holes do I have in this region? Negligible. So the problem is that I have negligible holes here, and therefore I'm not going to get much holes flowing from right to left here. And similarly, I have negligible electrons here. So I'm not going to get many electrons flowing from P to the N side here. Right? And therefore, the amount of holes flowing from N to P or from electrons flowing from P to N is going to be very small. And that's why the current is going to be very small. I don't have enough holes here and I don't have enough electrons here. And therefore, the current has to be small. So that's the reason why you find that once you apply reverse bias, the current that flows in the circuit is a small current here. Okay? So because of very few electrons in P type and holes in N type, current is very, very small here. The other thing that we know is the application of reverse bias. What does it do? It, as I said, it increases the electric field. Increases the electric field means what? Increases the potential drop between P and N region here. So this is the picture that we have earlier. The one between the black lines here, that's at equilibrium. And we have this built-in voltage here. When we apply a negative bias, what happens is electric field increases, depletion width increases. So depletion width goes to these red lines here that you see here. It has expanded. And my total potential drop across the PN junction will be equal to the earlier drop, VBI, plus whatever is the reverse bias that I apply. Okay? So my net drop across the junction increases to VBI plus VR. Under forward bias, the net drop across the junction became VBI minus VF. It was becoming smaller. In this case, it is becoming larger. Okay? Alright, so I have a video here. I'll explain why I've put it. Let's see this video. Okay. Alright, how is it relevant? It's relevant because, you know, what you're seeing here, what it illustrates are the first impressions. The first impressions get deeply imprinted. And that's why, you know, I'm putting these pictures here, right? I'm putting these pictures here and you learn some of these things you're seeing for the first time and they'll get imprinted in your memory. And many times what happens is those first impressions become very resistant to change. You carry it for a long time, right? And for example, I wanted to caution you that I've put these pictures here. It shows voltage changing like this here, right? Voltage changing from here to here like this here. This is a very simplified picture. The actual voltage that changes in the depletion region is not linear. It's not linear. It will change in a more complicated manner. If the doping is uniform, it will change in a quadratic manner. If the doping is non-uniform, it may change in a more complicated manner. These are schematic drawings and, you know, some things I'm not saying it explicitly, but these are schematic drawings. The only thing that you carry from this particular picture is the voltage drop initially is VBI and the voltage drop after that becomes VBI plus VR. Don't carry the fact that you see it linear. It is not linear. So similarly, there are a lot of schematic drawings that we draw and what I say about those drawings, you can take it, but there are many things that you will see in the drawing and you may take an impression which is not intended. Okay? So, so this red line, I mean, it's not linear. Okay? So similarly, there are a lot of schematic drawings. PN junction, all of us know, it's not like this here. It's not a rectangular bar. It's not like this. I showed you earlier a more realistic picture of a PN junction. Okay? So these are all schematics. And as I said, all representation is for a purpose. And in this case, my purpose is just to show you that I have VBI here and VBI plus VR here. Okay, so don't read too much into this picture here. Depletion widths are also, you realize, are not very sharp. I've drawn a boundary. Nothing is sharp in nature. So what you have is you have a more gradual transition. It's not that you have a neutral region here and then suddenly you have charged region here. It doesn't happen like that. The region here, there's a transition region. The charge gradually goes down to 0 and the region becomes neutral here. So these are not very, very sharp boundaries. So these are simplified pictures. Their aim is to convey a certain concept in a certain manner here. Okay. All right. So let's come back to our IV characteristics. So, as I said, we'll not derive these things. We'll only state the model here. So when I take a PN junction, and PN junction's characteristics can be modeled as an exponential characteristics here. I equal to IS. IS is called the reverse saturation current. Exponent VD by NVT minus 1 here. VT is what we call as thermal voltage. KT by Q, 26 millivolt here. And N is what we call as the ideality factor. If N happens to be 1, we call it as an ideal diode. Many times N is 1, many times it's 2 as well. And in most diodes, what happens is it may be 2 at low currents and then gradually become 1 at higher. Okay, so N could be a function of voltage as well. So, but in simplified models, we neglect N and we simply say I equal to IS exponent VD by VT here. But N is usually there. Okay. All right, so forward bias. Most of the time we apply a forward bias which is considerably larger than the thermal voltage, which is 26 millivolt here. So minus 1 can be neglected here. And therefore, it's a exponential characteristics that you see here. Okay, so you get a nice exponential characteristics. Note that every model will break down at certain point here. You see a breakdown of the model here. It's a nice exponential here. It breaks down here. The current here in a PN junction is limited more by leakage. There are various sources of leakage here, so it's not that exponential here. Okay. Similarly, if I go to very high currents, I will find that this it will deviate from the straight line here. It will deviate from the straight line and it will start leveling off. And that happens because of other resistances in the PN junction diode here. So in between, you have this nice exponential region here, which on a semi-log axis shows up as a straight line here. But at lower currents and at higher currents, again, it will deviate. The model will deviate from this exponential here. Reverse bias, most of the time we apply a reverse bias, which is much larger than VT here. So when we apply VD equal to minus VR, then you note that I will simply become to minus IS here. And so under reverse bias, the current that flows is the IS here, and that's called the reverse saturation current. In many diodes, what may happen is that if you actually go and measure the current under reverse bias, you will not find IS. You will not find IS, you will find a current which is much larger under reverse bias condition here. Okay, so don't be surprised if you go to the lab and you see a diode. So what you do is, let's say you take the forward characteristics here. Say forward characteristics is here, and you fit this particular expression and you calculate IS, right? If you measure the data here and you fit this exponential, you can find out what is the value of IS, right? And then what you do is, you go and take a diode, measure it in the reverse direction. You would expect reverse saturation current to be IS. You may find reverse saturation current is several orders of magnitude higher. So what you may find is that this model, you may have one IS for the forward bias and a different IS for the reverse bias. Okay. In simplified models, we say some diodes may follow this, but in many diodes you will find that the reverse current, actual reverse current flowing in the diode may be different from this IS that is there. Okay. So I'm just cautioning you that in the simplified model, it indicates that the current is minus IS. It may not be. In real diodes, the current may be much larger. The point is, the current is largely independent of bias. The current that you see here is a constant current, doesn't depend on voltage, and that is indeed true up to a certain point. Up to a certain point, what point? Breakdown voltage here. If you apply a large enough voltage, what you find is that the current under reverse bias becomes, after a while, very large, and we say that a breakdown has occurred in the diode. And breakdown voltage that you see here, this diode has a smaller breakdown voltage. This one has a larger breakdown voltage, and it depends on how you make the diode. If the doping density in the diode is very high, then typically you find the breakdown voltage is low. On the other hand, if doping is low, you find breakdown voltages are high. So breakdown voltages can be as low as 10 volt. It could be as high as 500 volts. So it depends on how you design this particular diode here. Now, so a little bit on how does this breakdown occur? Why does it occur? Okay. So to understand this breakdown, you have to look at a process called impact ionization. Impact ionization, so let's look at, again, these are very simplified pictures. Don't read too much into it. Okay. It's not that I have a lattice and I have a free electron moving around inside the space, that there are empty spaces in the lattice and then the electron is only able to move in the empty spaces. That's not the picture that I'm painting. Okay. Electron is not moving in the empty spaces. Electron is moving in the energy band. All right. So as I said, don't read too much into these diagrams. Focus on the main concept that I'm trying to tell you. So here is an electron, and suppose I apply a reverse bias. So the electron will gain energy from the field, and what may happen is the following. This electron moves, right? And what does it do? Look at the word ionization. What does ionization mean? Ionization means you eject an electron, right? When you ionize a gas, what do? You eject an electron from the gas atom, right? So what happens is, note this electron, it's moving with some energy, and there's an impact here. Simplified picture, again, keep that in mind. There's an impact between the electron and the silicon, and what it does is, it ionizes the silicon and creates a free electron, and it creates a hole. So this process, so what we are saying is, an electron moving can create another electron hole pair. That is what happens here, another electron hole pair, because the electron transfers a part of its energy to the lattice. Okay, and thereby creates this electron hole. Now what happens is, this electron will also move, and this undergoes an impact, and it creates an electron hole. And this process can then, what happens is, if this process becomes sufficiently large, then I get a lot of electron hole pairs, right? A lot of electron hole pairs, and then I can have very large current flowing in the reverse bias direction. So let me illustrate that further. So here I was just telling you what impact ionization is. An electron with a sufficiently large energy can cause generation of an electron hole pair, and that process is called impact ionization. Okay, so let's look at that. So we are talking about reverse bias. And in reverse bias, remember we said the current is very low. Why? Because there were very few holes here. The holes have to flow from N to P, and electrons have to flow from P to N, and there are very few carriers. So the reason why current is very low is I have very few carriers, okay, that can move in the right direction here. So now let's see what happens here. This electron starts from here. Very few electrons are there, fine. This electron starts from here. As it moves here, you note that there can be a large electric field. So what happens is, this electron accelerates and gains energy. If it gains sufficient energy, what can it do? It can create impact ionization. And now what do you get? You get two electrons. So my current was very low because only one electron could move to the N side here. But now I get two electrons. And now both these electrons will move. And now what happens? These two electrons here, they also create electron hole pair. And now I get 4 of them. And now these will move. And I may get 8. Now you see a multiplication is occurring. From 1 I get 2, and 2 to 4, and 4 to 8, and 16, and all that. And this multiplication process can become really huge, so that what I may end up with is very large number of carriers. And now not only that, look at these holes here. What will happen to the holes? The holes are going to move left. So the holes are going to move like this here. The holes are going to move. And what will these holes do? They will also cause impact ionization. Right? So you end up with these electrons here. Now these electrons will again move here. So what you're seeing here is that you're getting a lot of multiplication process. And then you can have an avalanche of carriers. Lot of carriers actually. So all these electrons that are generated, they will all move to the N side. All these holes that are generated, they will all move to the P side. And suddenly you have a lot of current. So the current was earlier limited because I didn't have enough holes here. I didn't have enough electrons here. Now these plenty of electrons and holes are being generated through what? Through a impact ionization process. Okay. So this process is similar. We call it an avalanche mechanism because all of you know that you can start with the avalanche with a little bit of snow falling, and then it gathers more snow and the whole thing blows up, right? And that's what really happens here. This whole thing from 1 electron to 4 and 16, and then eventually you can have thousands and hundreds of thousands of electrons coming out. And that's what we call as breakdown. So this is the mechanism of avalanche breakdown. Now note, this process will occur only if impact ionization occurs. And to create impact ionization, I need sufficient amount of electric field. So that's why the breakdown will occur. If I go back, breakdown will occur after a certain voltage. Because as I increase the voltage, the field in my junction is increasing. Once it reaches a critical field, then impact ionization starts, and then I start getting a breakdown. And then I start getting a breakdown. Okay? So that's what is happening in a PN junction. Avalanche breakdown. There's another breakdown that occurs, which is a different process, which is not impact ionization, but which we call as a ionization due to field. Now, impact ionization, realize what impact ionization is also to some extent is due to field, but the process is my electron has a large energy and it transfers that energy to the lattice. So impact ionization is occurring because energy is being transferred to the lattice. While in this case, what is happening is the electric field is large. So what electric field does is it just pulls an electron out. Pulls an electron out from the lattice. So it's not that an electron is moving, transferring its kinetic energy to the lattice and then knocking out an electron hole pair. No. What is happening is a very large electric field is just ripping the electron out from the lattice here. Alright, so no kinetic energy is being transferred. It's just ripping it off. Very large electric field. Because remember, an electron is held to the lattice by what? Electrostatic forces. And if you have a very large electric field, it just pulls it out. Right? So this is a different kind of an ionization. And if this ionization also becomes large, then I will get, now this is this ionization that you see here. Right? So if you have an electric arc, normally if you apply a sufficiently large field, the field rips the electron out and the whole region becomes charged and you get a current flowing between two plates, let's say, two plates which are kept closely spaced in air, let's say. Right? So this is what we call as a breakdown mechanism. We call it as a Zener breakdown mechanism. The earlier one was called avalanche breakdown mechanism, where the impact ionization was important. And here is the Zener breakdown. And that occurs when you have very, very high electric field. When you have very high electric field, then this Zener breakdown mechanism occurs here. Okay? So impact ionization occurs. Not impact ionization, ionization due to field. So these are just happening here, all these places, they are happening here. Alright? The field is ionizing and all of these will move here, all of these will move here, and you get a lot of current flow. So two different mechanisms of breakdown. One is avalanche breakdown, the other one is Zener breakdown. And the most common breakdown mechanism, most of the diodes that you see in the lab and that you'll handle, they all break down because of avalanche breakdown. But interestingly, they will all break down due to avalanche mechanism. But many of the diodes that you see in the lab, they're called Zener diodes that you've studied. And they're called Zener diodes, but the breakdown mechanism is actually avalanche. So there are diodes in the market which go by the name Zener diodes, but the breakdown mechanism is avalanche. It's not Zener breakdown mechanism here. Alright, so the most common breakdown mechanism then is avalanche mechanism. Okay? In some diodes, you may see Zener breakdown. Alright, so that's as far as the behavior of PN junction is concerned. And let's look at the models now. Now, in the forward bias, what we are saying is the PN junction can be modeled as these three elements. Do they make sense? Under forward bias, what happens in the diode? A current flows, right? And I'm modeling it as a current, this current here, which depends on the voltage here. Alright, so this is this current. Apart from that, we know a PN junction has two capacitances in it. One is a junction or depletion capacitance. The other one is a diffusion capacitance. So these are the two capacitances that are there here. Okay. Now, for DC, when I'm handling DC circuits or very low frequency circuits, capacitances do not matter. And we think of diode simply as this exponential diode that you see here. Right? But when frequencies become high enough, you know that this part can also carry now significant current because the impedance of this path is 1 by omega c. And if frequency becomes high, the impedance of this path becomes low, and increasingly current starts flowing in through these capacitors here. Okay, the capacitors become important as I go to higher frequencies here. Now, what are these capacitors? The first one, as I said, is because of depletion region. And the second one is due to diffusion. So depletion or junction capacitance is because we said that there is a depletion charge here. As you change the voltage, for example, if I increase the voltage here, forward bias, depletion width shrinks, electric field goes down, charge goes down. And we define the capacitance as, capacitance is always positive, so we define it as Cj equal to minus del Qj by del Vf. Minus because the charge is going down in response to voltage here. Capacitance is a positive quantity, so we put a minus here. So that's a capacitance associated with this one here. And we have a model for this particular capacitance. This is important from a circuit designer's perspective now. This depletion capacitance Cj is equal to Cj0, 1 minus Vd by Vbi to the power m. So let's understand all these terms here. Cj0, as you can see here, is the capacitance at zero bias. Vd is the voltage across the diode, or the voltage applied to the diode. Okay, the external voltage that you apply, that's the voltage here, Vd. Vbi is the built-in voltage, and m is a parameter which we call as grading coefficient, is related to how PN junction is made, related to the doping profile. Okay, many times it's 0.5, sometimes it's 0.33, so this is something that varies here. So, you know, when you, let's say if you're interested in a particular diode, say 1N4007, so what you do is you go to the manufacturer site, they will give you the data sheet. And in the data sheet, you can get these values here for that particular diode. You can get the zero bias capacitance here, you can get the built-in voltage here, and you can get the grading coefficient here. So depending on which diode you're using, these values will be known to you. Cj0, Vbi, and M are known to you. Which means that, you know, for any diode in a circuit, all I have to know is what is the voltage across the diode. And once I know that, I can calculate the depletion capacitance. So it depends on these three values here, Cj0, Vbi, and M. Now this equation that I've said is valid for both forward and reverse bias here. The only thing is, in forward bias, Vd is positive, and in reverse bias, Vd is negative. Alright, so what you will see is the difference here. Another one is Vd in forward bias. Note that I told you Vbi is roughly around 0.85 or so, and Vd, forward bias voltage, is always less than the built-in voltage here. It may be 0.7, it may be 0.6, it may be, you know, it never exceeds Vbi. That's another misconception maybe that I should emphasize to you. This is a good point to talk about it. So when, alright, frequently, you know, we hear from students that the current in a PN junction, so you know, many times when we ask what happens in a PN junction, how does it conduct? So a frequent response from students are, I don't know where it comes from, but they've read it somewhere or what. So they say that there is a built-in voltage here, 0.85, right? So first misconception that many students carry is that the built-in voltage is 0.7. That inside the diode, there is a built-in voltage which is 0.7, right? And then they say, well, when you apply a voltage here, and you apply a voltage which is 0.7 or so, a little larger than that, there is no barrier inside the diode, and then the current flows. Alright, so this is a very mistaken conception. That's not what happens here, right? It's not that so what happens, that what I want to clarify is that the voltage inside a PN junction is VBI, built-in voltage. And it's not 0.7, its value depends on the doping and all that. A better value would be, let's say 0.85 volts. And what happens is, you never overcome this built-in voltage. It's always there. It's always there. When you apply 0.5 volt, if the inside voltage was 0.85, the net voltage becomes 0.85 minus 0.5. And the voltage becomes less and the current begins to flow. When you apply 0.7 volt, the net voltage inside the diode is still 0.85 minus 0.7. So it's about 0.15. You never overcome the entire voltage here. It's always there. Alright? Why is it always there? The question that may arise in your mind, Can't I apply 0.85? What if I apply 1 volt? Will I make it negative? What happens is, note that as you apply this voltage, which is higher and higher, what is happening is more and more current begins to flow, right? So when you have 0.7, let's say, the current is fairly large. Now let's say you make 0.75. How is the current increasing with voltage? Exponentially, remember. So the current is increasing exponentially. So the current becomes very large. And what happens? As the current becomes large, more and more voltage gets dropped here in this P region and this N region. Earlier, what happened was most of the voltage was dropping across the junction. That was the bottleneck. But as the current increases, this is no longer the bottleneck that much. And the current starts to drop in the P region here. And it drops starting in the N region here. So increasingly more and more voltage gets dropped in P and N, and you're not able to. So when you say, suppose I do apply 1 volt to the diode, well, 1 volt is not going to drop here. Most of that excess voltage is going to drop here and here. And the voltage across the junction may still be 0.1 volt. Okay? So when you apply 1 volt, you don't overcome the built-in voltage. All right. So when I say that this voltage that I've applied goes all the way and appears over here, that's only true up to a certain point. Beyond a certain point, what happens is more and more of this voltage gets dropped here in P and N region. And that's the reason why what happens is the current that I've drawn here, if you look a little closely, it's not showing you, the current increasingly starts curving. It's no longer exponential. And why does it curve? It actually curves because it increasingly becomes linear. It's no longer exponential. It tends to become linear. And a linear graph, in a linear relationship on a log axis will look like as if it's curving like this here. And why is it becoming linear? Because more and more voltage is dropping across P and N region, which are like resistors. A normal P-type semiconductor is a resistor. A normal N-type semiconductor is also a resistor. So when drops begin to occur across P and N region, the diode is becoming increasingly resistive. Okay, so keep that in mind. I thought it was before I leave this particular topic, should remind you of that misconception. Okay, so let's come back here. So that's the depletion capacitance then that we have inside a PN junction. The other capacitance that we have, as I said, is diffusion capacitance. I have my diffusion charge here and I have a diffusion charge here. Now note, this diffusion capacitance is there only under forward bias. It's there only under forward bias because under forward bias, I injected a lot of holes here. And under forward bias, I injected a lot of electrons here. The QP and QN are there only in forward bias. In reverse bias, there's very little current flow from here to here. There's very little charge. Okay, so this diffusion capacitance is there only in forward bias. And diffusion capacitance will be, again, rate of change of charge with respect to voltage. That's how we define diffusion capacitance. And one can show the diffusion capacitance is directly proportional to the current. Because note that current results from injection of charge. And capacitance is also due to that same charge. So one expects a relationship. So diffusion capacitance CD is equal to IF, the forward current. This is the thermal voltage. And this is a parameter which we call as the transit time. It's related to recombination parameters, related to other things here. So it's a parameter again, which you can find from the manufacturer's data sheet here. So tau is one parameter of a diode. And once you know that, you can calculate the diffusion capacitance. So that's another capacitance to keep in mind here. All right. So that's the picture of my diode under forward bias here. I have this current that you see here, and I have this capacitance here, depletion capacitance, and I have diffusion capacitance here. Now, how many parameters do I need to describe my diode? Every model has a set of parameters. So, suppose I give you a diode and you want to use it in a circuit. You have the model, right? You have the equations. To use the diode, what will you ask me? Give me the value of IS. So all diodes will have this particular model. What will differ from one diode to the other is the parameters. So you will ask, give me the value of IS, give me the value of N, and maybe give me temperature. Then if you give me all of that, I now know and can calculate what is the current. So I need how many parameters here? 3. And how many parameters do I need here? CJ0, VBI, and M. So 3 parameters here. And how many do I need here? Tau. So how many parameters do I need? 3 plus 3 plus 1. So I need 7 parameters at least. So if I give you these 7 parameters, now you're in a position to use this particular diode. You know how the diode behaves. How much is its capacitance, diffusion capacitance, junction capacitance, its current. You can calculate all of that. So every model will have a set of parameters here. So all my PN junction will have this particular model, this mathematical structure. What will differ from one diode to the other are these parameters. Now, more complicated model will have, more complicated mathematical equations, more number of parameters, and the model will become more complex. It's not that this is the only model that I have. Okay. All right. Reverse bias. In reverse bias, we said the current that flows under reverse bias is the reverse saturation current and is constant, independent of voltage. Now, this model that we are building is below breakdown voltage. And in addition to that, we have a junction capacitance, CJ. That's it. I don't have any diffusion capacitance here. Okay. Now, this is interesting because normally we say that under reverse bias, my diode does not conduct. My diode does not conduct because the saturation current is very low. But note, under reverse bias, under transient condition, I can have a lot of current because my capacitance is there and capacitance could be discharging. Right? So I could have current under reverse bias, which is significant because of this capacitance here. Under DC, current will be very low, but under transient conditions, the capacitance can be large. I mean, the current could be large here. So let me illustrate that. So this is something that you could do in the lab. Let's say I have a very simple circuit, 1K here, 1K here. You apply a square wave. If you apply a square wave, 505, well, you'll get current 2.5, 0, 2.5, right? Straightforward. Now put a capacitance here. Now what do you get? We agree the current initially may go high, 5 milliamperes. The moment you, let's say you go to, here of course is going from 0 to 5. So the moment you go from 0 to 5, capacitance acts as a short and the current becomes 5 milliamperes. And then the current drops to 2.5 here. Now when you go to 0 here, this capacitance discharges and therefore you get a current here, right? You get a reverse current. Why? Because of this capacitance here. Now I want to show you, so this picture, and I want to show you a diode. If I take my diode and I do this experiment on the diode, I will see something similar. What do I see here? I see diode conducting in the reverse direction. And why is it conducting in the reverse direction? Just to use this as an analogy, this capacitance here. Inside the diode also I have a capacitance, as I said. And that capacitance is discharging. And so it is this capacitance which is discharging here. Okay? And therefore you can have a current in the reverse direction, but only momentarily. Once the capacitance is discharged, then the current is gone. But for a short duration, I can have significant current. Okay? Now remember, what will happen is the following. When I apply a 5 volt, the 5 volt will cause a current to flow. The diode is forward biased. In forward bias, what do I have? How many capacitances? I have a depletion capacitance and I have a diffusion capacitance. Now this diffusion capacitance, I forgot to mention, has a very large value. Compared to depletion capacitance, for example, in some of homework assignment, you'll work it out. Depletion capacitance may have a value, let's say 1 pF, 1 picofarad. Diffusion capacitance may have a value of 1 nanofarad or 10 nanofarad. Diffusion capacitance is much larger. So now what happens is, think about it. I have a capacitance here, which is depletion capacitance and both diffusion capacitance. Depletion capacitance doesn't matter because in the forward bias, because diffusion is much larger. So I have this diffusion capacitance which is all charged up, right? It's all charged up. Now when you make it 0, now this diffusion capacitance has to discharge. And as it discharges, it pumps in all this current here. Now you can also now think that what if I change this voltage rapidly? What will happen? Suppose I change it rapidly so that it's right here. The frequency is right here at this point. I switch it off. What will I see here? I will see almost like a square wave here. This one will be like a square wave because before it discharges, I go to the next cycle here. So I will see as if the diode is conducting very large current in reverse direction also. You will not see this particular part here if the frequency is high. Okay. So that's the reason why I was telling you is that when I apply a sinusoid here, and if the frequency of the sinusoid is very high, the diode is going to conduct both for the positive cycle as well as for the negative cycle. Negative cycle is conducting because of the capacitances here, and therefore it will not rectify. The diode will fail, all because of the capacitances which are there inside. Now you may say, can't I eliminate the capacitance? Well, if you eliminate the capacitance, what else do you eliminate? If you eliminate the capacitance, you eliminate current also. It's a part and parcel of the diode. The current is flowing because of charge, and the capacitance is also coming because of charge here. So if you want current to flow, you will have charges inside, and you want current to change with voltage, and therefore the charge will also change with voltage. So it's part and parcel of the diode here. All you can do is make this tau small. As I make my tau small, now capacitances become smaller. So when we say there is a fast diode and there's a slow diode, how do they differ? They differ in tau here. A fast diode will have tau which is very small, and a slow diode will have tau which is large. And that's where the differences in speed come from. They alter the amount of diffusion capacitance that you see here. Okay. Alright, so this is showing you what happens in a diode here. If you switch, the diode will conduct for a certain time in the reverse direction and then switch off here. So it takes some time for a diode to switch off. And that is what is responsible for diode conducting large current in the reverse direction here. Okay. So that's an important point. The diode can conduct in the reverse direction, but momentarily. And for how much time? For a time that you see here, which is related to my transit time of the diode. So of that order of magnitude. If my transit time is, let's say 1 nanosecond, my diode is going to be conducting for a few nanoseconds. If my transit time is milliseconds, my diode is going to be conducting for milliseconds. So it's all related to the transit time of the diode here. So very, very important parameter which tells us this property here, that how long will my diode conduct in the reverse direction here. So if you want to make a rectifier, and let's say the rectifier works, you want the rectifier to work very well at 1 megahertz frequency, right? So how will you go and choose a diode now? There are a variety of diodes available in the market. How will you choose a diode? It has to work as a rectifier at 1 megahertz. What will you do? 1 megahertz means what? 1 microsecond. So you're going to go and choose a diode whose transit time is much smaller than the 1 microsecond. So you're going to choose a diode with transit time much smaller than 1 microsecond, maybe 1 nanosecond. Because the diode is going to be conducting only for 1 nanosecond. And 1 nanosecond is a very short period compared to the time period which is 1 microsecond here. So you're going to choose a diode like that. Okay? So that's telling you how, if the rectifier is an application, how do you choose a diode? Okay, so tau or transit time is an important parameter here. Okay, so the next thing is, so we have seen now what a model looks like, and we know the model that we have is a model which is accurate, but it's not suitable for circuit analysis. Why? Because if I use an exponential model here, exponential diode model here, I end up getting a nonlinear equation, and solving a nonlinear equation is difficult, right? So the model that the exponential diode model is more suitable for circuit analysis, for using simulations. If I have a simulator, there I can use the exponential diode model very easily because I'm doing numerical analysis using a computer. While if I have to do hand analysis, then you know that the exponential diode model is not that convenient, and we need a simplified diode model here. So I've already talked about what you want to do is approximate the diode by you can approximate it by a battery, or you can approximate by a battery and a resistor. So you can have those kinds of models that are there. Okay. So the next couple of slides that I had was, if you had a nonlinear model, how would you solve it? Well, using iterative method is one, right? Iterative method is what? What will I do? I guess a value. So I'm assume. So this is these are the two equations that you have to solve. Okay, so let's stop here. We'll continue.